I'm in between you and your coffee. So I'm presenting, I'm Tyler, I'm presenting generalization under gradient descent via deterministic PAC-Bayes, which is joint work with Eugenio at the front here, and our collaborators, George, Benjamin, and Arnaud. Yeah, so the setting you're quite familiar with, so I can be quick here. So we have a loss function L, which maps a hypothesis from the set H, and an example from the set Z to a loss. The classical, we're going to take H to be in RD. So the classical example is like well, one example is a neural network FH. So H here is the weights and biases, and the examples are some features and a label. And we're interested in minimizing the population risk against some measure mu. And we have access to finitely many data, which we represent with the data set S. And then we have the empirical risk here, which we write as LS. The objective here is to control the population risk using properties of the learning algorithm. And the properties of the learning algorithm we're interested in this paper is the optimization scheme used. So typically, especially with neural networks, you use some kind of version of gradient descent. So the continuous form of this is given by this gradient flow here. So this is the gradient flow against the empirical risk. And then we also have the discrete dynamics here. Typically some variant of this, like SGD, momentum, or something more complex like Adam is used. And so the question is, what role does this optimization algorithm play in promoting generalization? And can we relate it to the geometry of this function, the empirical risk? Okay, so we're interested in developing some PAC-Bayesian bounds. So these are high probability bounds, or bounds that are high probability in the data set, that relate the generalization gap, the difference between the population and empirical risk, to the distance between posterior and prior. And people really like these. They're non-vacuous for deep neural networks, so that's very exciting. And they also hold in high probability and can often be computed in practice, which is not always the case for these bounds. However, they have some drawbacks, right? So for non-stochastic algorithms, they can be difficult to use because this KL term can be difficult to control, sometimes can be non-vacuous, or vacuous rather. And this can be resolved either by modifying the algorithm, injecting some more noise into it so you can control this, but this deviates from what's used in practice, right? You're modifying the algorithm. Or you can use this technique of de-randomization, where in the analysis you add some noise, and then you control the difference using some stability properties. But this stability property comes at the price of some assumptions and maybe a slightly more complicated proof. And thirdly, the bound is in expectation with respect to the posterior, which is not always possible to compute. So in this work, we look at disintegrated PAC-Bayes bounds. So these are bounds that hold in high probability with respect to both the data set and the sample from the posterior, right? So there's no integration over the posterior. And so an example here from Universitat is a bound like this. So you replace the KL term with this ratio between the posterior and prior. Yeah. And then the second technique involved in our approach is utilizing the randomness provided at initialization. So we have a deterministic algorithm. We make sure that's not a problem by using the randomness in initialization, by treating this kind of flow as a flow in measure space according to this push forward. Okay. So what do we get from this? So this is the main result for the continuous time algorithm. So very simple assumptions. We assume that L is R sub Gaussian under mu and is twice differentiable. And with this alone, we can bound the population risk by the empirical risk as well as this stuff. So what is this stuff? So this term here is basically the curvature over the trajectory. So we integrate over the curvature. And then this second term here is just a ratio based on the initialization distribution. So for example, if we use a Gaussian initialization, it's just the difference in the norms. Yeah, so what we've effectively done here is obtained a bound that's entirely computable using the optimization trajectory. No integration required outside of over the trajectory. And furthermore, you can get faster rates using these KL PAC-Bayes bounds. Move past that. So yeah, the main thing we've done is effectively bounded the generalization gap using this curvature term, which depends only on local properties of the loss and can be estimated using like a Hutchinson's trace estimator. But the nice thing about this is it also feeds into this folkloric connection between flat minima and generalization that Maxime just spoke about earlier on. So yeah, so that's an exciting connection as well. For the discrete time dynamics, it's again very light assumptions. We just need, again, R sub Gaussian and twice differentiable. And on top of that, we need smoothness, so Lipschitz gradients, and a sufficiently small step size. And in this case, we get a very similar bound, except we replace the curvature term with this sum. And as you might expect, when the step size is small, this term basically becomes the curvature, the Laplacian. So just for the sake of intuition, we look at some examples where you can actually compute these terms. So we look at the random feature model with Gaussian weights. And in this setting, you can show that as you send the number of features to infinity, you can bound this with something that's just O of t. And this, of course, means you have a trade-off with t between the training error and this generalization bound, which we show in this specific case with polynomial feature maps. You can get a bound with log m over m. Similarly, for wide neural networks, you can show that when the network's wide enough and with the appropriate scaling, the assumptions of this discrete time bound actually hold with high probability. And that this term here, if you're scaling the step size correctly, you can bound it by the trace of the NTK. Okay, maybe I'll skip the proof sketch, but roughly speaking, the proof basically involves using Markov's inequality to bound this term here. When you integrate against this logarithm term, cancels out the posterior, and you just get the prior here, which allows us to use subgaussianity and obtain this bound. And then with this bound, you have everything you can compute just using the optimization trajectory, aside from this term. We don't have the posterior explicitly, right? So to control that term, we use the continuity equation, which allows us to say how the measure under gradient descent or gradient flow evolves. And then with the chain rule, we can easily obtain something like this. So it's fairly lightweight proof. And it's something we're quite pleased about because it means we can very easily extend to other algorithms. So for example, if we consider this iterative scheme given by a time-dependent vector field, then we get the same result. As long as this vector field is M Lipschitz, we can have something like this. And this allows us to target other algorithms, such as ones that with dynamic learning rates, stochastic mini-batching, momentum, and Hamiltonian dynamics. So just quickly, I mean, in the paper we talk about this in detail, but for example, with the momentum dynamics, where you have this velocity term, you can get a generalization bound, which, funnily enough, doesn't depend on anything except the start and end iterates, as well as the momentum coefficient. And also for the Hamiltonian dynamics, you can get a similar bound, which, yeah, you can check out in the paper. Yeah, so to conclude, We developed disintegrated PAC-Bayesian bounds for iterative optimization schemes. Our bounds relate the generalization gap to the curvature along the trajectory. And we do this with a fairly flexible proof that can easily be applied to a range of different schemes. Thank you.
This is a question maybe not about your paper in particular, but are there problems other than deep learning where we care about flat minima? And the only context that I've seen the flat minima appear is in deep learning, but what are the properties of deep learning that of the deep learning problem where we care about flat minima?
Yeah, it's a big question. Maybe one to unpack at the poster, but I guess I'd say shortly that the idea of flat minima being a thing that promotes generalization has actually been an idea that's around for a while before deep learning really properly took off. So it's definitely been a thing statisticians have been exploring. I think the reason it's become so attached to deep learning is because it's been observed in practice that you do genuinely converge to these flat minima. But yeah, we could talk about it more later maybe.
Right. I think it's time to break for coffee.